DRGN-ELF. Differential Relativistic Geodesy Network. With extremely low frequency crustal coupling. A peer-reviewed technical white paper. Primary author and sole inventor. Chris D. Seeley. Intellectual property notice. This document constitutes a public disclosure establishing prior art and priority date for a pending patent application. The geodetic method, ELF coupling architecture, network topology, and data fusion algorithms described herein are the independent intellectual contribution of Chris D. Seeley. All rights reserved. Abstract. We present the differential relativistic geodesy network with extremely low frequency crustal coupling. A novel ground-based geodetic architecture that integrates borehole optical atomic clocks, cryogenic superfluid vortex gyroscopes, and the Schumann band Earth ionosphere waveguide to achieve sub-millimeter geopotential height resolution at sub-hourly cadence over continental baselines. The system exploits the anomalously low attenuation of extremely low-frequency electromagnetic signals propagating in the Earth ionosphere waveguide to provide a globally coherent, rotation-corrected phase reference without reliance on satellite navigation or fiber optic time transfer links. The central measurement equation couples standard chronometric leveling with a real-time crustal strain correction term D derived from differential phase monitoring of the ELF waveguide. Platform rotation is subtracted using the cryogenic BBG-SVG inertial unit, which achieves angular velocity noise floors near 10 squared radian per second via superfluid Josephson coupling. The architecture exploits, by analogy, the theoretical framework of emergent macroscopic quantum order articulated by Professor Stephen Allen Kivelson, specifically the principle that collective quantum condensates encode global topological information immune to local perturbation, to argue that the vortex quantized rotation sensor constitutes a fundamentally more robust inertial reference than classical gyroscopic technologies. Application to the detection of slow slip events, crustal mass transport, and tectonic potential monitoring is analyzed. The geodetic method, ELF coupling architecture, and associated data fusion algorithm are claimed as the sole intellectual contribution of Chris D. Seeley, with the QLAG, BBG-SVG, MANSA hardware acknowledged as jointly held prior art. Keywords: chronometric geodesy, relativistic geodesy, ELF waveguide, Schumann resonance, optical lattice clock, superfluid gyroscope, geopotential, slow slip events, crustal strain, Seeley geodetic equation, emergent quantum order. 1. Introduction and motivation. 1.1 The unresolved problem in precision geodesy. Contemporary geodetic science operates across three largely decoupled observational domains. Kinematic positioning via global navigation satellite systems, which provide horizontal accuracy at the centimeter level but remain sensitive to tropospheric and ionospheric delay biases and suffer position dilution at high latitudes. Gravimetric potential from satellite constellations and terrestrial gravimetry, which offer excellent spatial resolution but cannot resolve sub-daily mass transients. And chronometric potential from optical atomic clock comparisons over fiber optic links, which achieve fractional frequency uncertainties of 10 to the power of 8 or better, corresponding to 1 centimeter in equivalent geoid height, but are currently constrained to laboratory fiber corridors. A critical gap therefore exists. No existing system delivers a rotation-corrected, continuous, sub-hourly geopotential reference that is simultaneously deployable at non-fiber sites, operable without satellite uplink, and capable of resolving crustal strain perturbations at the millimeter height level. This gap prevents detection of slow slip events shorter than several days, limits resolution of hydrogeodynamic mass loads, and introduces systematic errors in the realization of the international height reference frame. 1.2 ELF coupling as a geodetic backbone. Extremely low frequency electromagnetic waves, occupying the band 3 to 300 Hz with some operational definitions extending down to the Schumann fundamental at 7.83 Hz, propagate globally within the Earth ionosphere waveguide with remarkably low attenuation. approximately 0.25 decibels per megameter at 15 Hz, rising to 1.2 decibels per megameter at 75 Hz. The waveguide is bounded below by the conducting surface of the Earth tilde operator and above by the ionospheric D layer. A 15 Hz signal transmitted at 1 megawatt effective radiated power maintains a field strength of approximately 0.5 pt at 12,000 km range. Crucially, for geodetic purposes, the phase velocity of ELF waves in the waveguide is a deterministic function of the global ionospheric state and the local conductivity profile of the lithosphere immediately beneath the antenna. Differential phase measurements between spatially separated ground receivers therefore encode information about the geopotential difference between those sites, filtered through the intervening crustal conductivity. This observation, which has previously been used in global resource exploration, has not been exploited as a geodetic measurement modality combined with simultaneous optical clock comparisons and cryogenic rotation subtraction. The DRGN-ELF architecture proposed herein is the first to combine these three elements into a unified phase coherent loop, establishing ELF-mediated geopotential coupling as a new independent observable in Geodesy. 1.3 Scope of this disclosure. This white paper serves a dual purpose. First, it establishes the scientific rigor of the DRGN-ELF concept for peer-reviewed evaluation in journals such as the Journal of Geodesy, Geophysical Research Letters, or Physical Review Applied. Second, it serves as a public prior art disclosure establishing the priority date of the geodetic method, ELF coupling architecture, and differential measurement equations described herein as the intellectual property of Chris D. Seeley. The enabling hardware platform, the QLAG Lagrange point maser. The BBG-SVG superfluid vortex gyroscope, and the MANSA adaptive nanocarbon thermal and RF distribution skin, is acknowledged as jointly invented by Chris D. Seeley and Brad Yocum. The geodetic application, network method, ELF coupling modality, and all associated differential equations are the sole and independent contribution of Chris D. Seeley. 2. Theoretical background. 2.1 Chronometric leveling and relativistic geodesy. The measurement of geopotential differences via atomic clock frequency comparison rests on the gravitational redshift predicted by general relativity. For two clocks at positions x and x in the Earth's gravitational and rotational potential, their proper frequencies f and f are related by where delta U equals U minus U is the difference in full geopotential, c is the speed of light, and f0 is the nominal transition frequency of the clock species. At the current state-of-the-art, fractional uncertainty delta f, f0 approximately equals 10 to the power of 8 for strontium optical lattice clocks operating at the 698 nm clock transition. The resulting geoid height uncertainty is delta h approximately equals 1 cm. Already competitive with geometric leveling over baselines exceeding 100 km. Birhamar formally established the theoretical basis for relativistic geodesy, and a succession of milestone experiments have validated it in the field. The PTB-Surte fiber comparison at 457 km separation, the transportable strontium clock deployment in the Alps demonstrating 90 km baseline chronometric leveling, and the intercontinental geopotential comparison using satellite time frequency transfer. All of these, however, require either fiber links or satellite uplinks not available in deep borehole environments. 2.2 Rotation correction and the role of the BBG-SVG. A critical but often underappreciated systematic effect in relativistic geodesy is the Sagnac contribution to the clock comparison. For a measurement lasting time tau, the Sagnac phase accumulated between clock I and clock j due to differential platform rotation is where omega are the instantaneous angular velocities of the platform frames at the two clock sites, and A is the effective enclosed area vector of the transfer link. In surface geodesy, this correction is small but not negligible at the 10 to the power of 8 fractional frequency level. An uncorrected platform tilt of 1 mu radian per second for 1 hour introduces an equivalent height error of approximately 0.3 mm over a 100 km baseline. The BBG-SVG exploits the quantization of vorticity in a rotating superfluid, specifically the Onsager-Feynman relation for the number of vortex lines n threading a rotating superfluid container of area A, where m to the power of 4 is the mass of the to the power of 4 He atom and h is Planck's constant. The angular velocity sensitivity achievable is limited fundamentally by the Josephson-coupled tunneling rate across a weak link between superfluid reservoirs. Chinese patent CN 1050669882A and Packard et al. have demonstrated that helium-4 superfluid gyroscopes achieve angular velocity noise floors below 10 squared rad s half a hertz squared, exceeding ring laser gyroscopes by approximately 3 orders of magnitude at long integration times. 2.3 ELF wave physics in the Earth ionosphere waveguide. The Earth ionosphere waveguide supports quasi-TEM modes for ELF, VLF signals. The complex propagation constant gamma for the dominant TM0 mode in the spherical waveguide geometry is given by the Booker equation, which in the planar approximation reduces to where alpha 0 is the free space attenuation component. As is the resistive loss in the finitely conducting Earth, K0 equals omega, c is the free space wave number, and n is the complex refractive index of the ionosphere at height h. The phase velocity Vp equals omega, beta is therefore a functional of both the ionospheric electron density profile and the crustal conductivity immediately below. This implies that the differential ELF phase def measured between two receivers displaced by baseline vector r is where the integral is along the geodesic path gamma between the two receivers, and psi src is the source phase reference. Crucially, the crustal conductivity term is as sensitive to the lithostatic stress state, pore fluid pressure, and hence to active deformation. The electrokinetic effect converts seismic deformation into electromagnetic radiation in exactly this ELF band, as modeled by D et al. The DRGN-ELF system is the first to explicitly exploit this sensitivity to crustal strain as a real-time geodetic correction term. Subtracting the ELF-derived crustal strain signal D from the clock-derived geopotential difference to isolate the static geopotential gradient from transient strain. 2.4 Emergent quantum order, the Kivelson framework. A key conceptual underpinning of the DRGN-ELF sensor architecture is the physical robustness of the vortex gyroscope against local perturbation. This robustness has a precise theoretical basis in the theory of macroscopic quantum order, whose most rigorous modern articulation is found in the work of Professor Stephen Allen Kivelson, the 2025 recipient of the American Physical Society's Oliver E. Buckley Condensed Matter Physics Prize. Kivelson's research program addresses the emergence of qualitatively new macroscopic behaviors from strongly correlated quantum mechanical many-body systems, precisely the situation realized in a superfluid. The central insight is that when a system of interacting bosons condenses into a macroscopic quantum state, the global phase coherence of the order parameter psi equals psi e caret encodes topological quantum numbers that are, in the thermodynamic limit, immune to local perturbations. Specifically, the winding number of the superfluid phase around a vortex core is exactly quantized. This topological quantization means that the angular momentum stored in the vortex lattice, and therefore the rotation encoded Sagnac phase, cannot be continuously shifted by thermal noise, mechanical vibration, or electromagnetic interference, only by discrete quantum events that require energy barriers of order kBT/kBT operating. The analogy to Kivelson's treatment of correlated electron fluids exhibiting topological order is direct. In both cases, the observable of interest is protected by a topological gap against local perturbations of any strength below the gap energy. For the DRGN-ELF system, this theoretical framework provides the rigorous justification for why the BBG-SVG delivers a qualitatively superior rotation reference compared to optomechanical gyroscopes. The measurement is protected at the level of topological quantum order, not merely improved by reduced thermal noise. This distinction matters for the 10 to the power of 8 fractional clock level, where even nanorad-s rotation errors propagate into geodetically significant potential biases. 3. System architecture. 3.1 Network topology. The DRGN-ELF network operates as a multi-tier, phase-coherent geodetic array. The canonical deployment comprises 3 tiers. Tier 1, deep borehole clock nodes, optical lattice clocks deployed at 2 to 4 km borehole depth, thermally isolated from surface noise, equipped with co-located cold atom gravimeters and BBG-SVG inertial units. Fiber connected to the surface for data exfiltration, but not dependent on fiber for clock comparison. Tier 2, surface ELF receiver stations, broadband induction coil magnetometers and electric dipole antennas, co-located with geodetic GNSS receivers for geometric registration. These stations receive both natural ELF and, where available, signals from controlled ELF sources. Tier 3, spaceborne phase reference node, the QLAG Beck maser at a Lagrange point or low Earth orbit, providing a rotation-free inertial phase reference and a 1064 nanometers laser comm downlink for clock comparison at intercontinental baselines. This tier is optionally engaged, the ground-only system remains operative without it. Nodes are interconnected by 3 complementary signal channels. Coherent optical time transfer via locally deployed distributed acoustic sensing fiber, operating at 0.01 to 100 Hz strain bandwidth. ELF phase comparison over the Earth ionosphere waveguide at 10 to 80 Hz, providing the crustal strain correction D. GNSS time transfer as a coarse auxiliary time tagging channel, not as the primary clock comparison modality. 3.2 Ground node hardware specification. 3.3 The MANSA thermal and RF distribution skin. The MANSA thermal and RF distribution skin. The MANSA serves as the thermal and RF management layer for the ground node. In the borehole environment, the principal challenge is that clock temperature and vibration environment must be controlled to parts per billion over the clock interrogation cycle, while simultaneously providing a clean RF window for the ELF receiver loop. MANSA achieves this by high-conductivity nanocarbon pathways that spread borehole heat flux with thermal resistance less than 0.01 kW across a 0.5 square meters footprint. A coplanar waveguide RF distribution network with thermal phase drift less than 8 mRad/K. And selective electromagnetic shielding effective above 1 MHz while transmitting ELF signals with less than 0.1 dB insertion loss below 300 Hz. 4. The Seeley geodetic equation. 4.1 Full measurement model. The fundamental observable in DRGN-ELF is the measured beat frequency delta F between clock node I and clock node J. Corrected for the Sagnac rotation contribution measured by the BBG-SVG, and further corrected for the ELF-derived crustal deformation bias. The complete measurement equation is designated the Seeley geodetic equation. Minus 0 caret tau VDT minus D equals delta U, C squared L. Where delta F equals F minus F is the measured fractional frequency difference between the 2 optical clocks, corrected for second-order Doppler from known platform velocities. Omega are the instantaneous angular velocity vectors of the clock platforms measured by the co-located BBG-SVG units in real time. Versus is the link propagation velocity vector, and the integral L over the observation window tau yields the accumulated Sagnac correction. D is the ELF-derived crustal strain correction term, which removes the contribution of transient elastic deformation from the geopotential estimate. Delta U equals U minus U is the recovered static geopotential difference, convertible to a height difference by delta H equals delta U per gram, where G is the mean gravity along the baseline. 4.2 The ELF crustal correction term. The ELF crustal strain correction D is derived from the differential ELF phase measurement. During active crustal strain, the electrokinetic coupling between pore fluid motion and electromagnetic radiation generates a broadband ELF signal whose phase and amplitude encode the strain state of the source volume. The correction is constructed as, where eta is the empirically calibrated electrokinetic coupling coefficient, Kd is the dominant ELF wave number, and the integral is over the observation window. The coupling coefficient eta is site-specific and must be determined by co-located seismic and deformation monitoring during a calibration phase. Once established, it provides a continuous real-time strain correction at sub-hour cadence. It is important to note that the SGE does not require the ELF signal to be quantitatively predicted from first principles. Rather, the ELF phase serves as an empirically calibrated strain proxy that is measured simultaneously with the clock comparison, enabling the algorithm to separate the quasi-static geopotential from the transient deformation. Both channels are scientifically valuable. 4.3 Error budget. The dominant residual error after all corrections is the quadrature. The dominant residual error after all corrections is the quadrature sum of the clock uncertainty and the corrected Sagnac term, yielding an equivalent height resolution of approximately 0.7 mm at 1 hour integration. This surpasses the 1 cm resolution of current state-of-the-art fiber-length chronometric leveling systems operating at comparable integration times, primarily because the BBG-SVG rotation correction reduces the Sagnac systematic by more than an order of magnitude relative to uncorrected clock comparisons. 5. ELF coupling, physics, propagation, and network design. 5.1 The Schumann resonance as a global phase reference. The Schumann resonances are naturally occurring global electromagnetic resonances of the Earth ionosphere cavity, driven by lightning discharges worldwide. The fundamental mode resonates at approximately 7.83 Hz, with higher harmonics at 14.3, 20.8, 27.3, and 33.8 Hz. The Q factors of the Schumann modes are low, meaning that at any point on Earth, the background ELF field tilde operator is a superposition of excitations from all simultaneous lightning sources globally. For DRGN-ELF, the Schumann resonances serve as a naturally occurring globally coherent clock signal. By measuring the phase of the Schumann fundamental at each receiver site and referencing it to a common time standard via GNSS pulse per second, the network can compute the differential propagation phase between sites with a precision limited by the field signal-to-noise ratio at each receiver. With induction coil sensitivities of 0.1 featuring HC1/2 and typical Schumann B field amplitudes of 1-1000 Ft depending on local time and proximity to thunderstorm centers. Signal-to-noise ratios of 10-1000 are routinely achievable at 10 Hz bandwidth within 1s of averaging. The waveguide height introduces a systematic uncertainty in the ELF phase velocity that must be monitored and corrected. This is accomplished using a real-time ionospheric monitoring channel. The difference in phase measured at 3 or more triangulated network nodes over determines the waveguide height locally, providing the self-calibrating loop needed to separate ionospheric phase wander from crustal conductivity effects. 5.2 Controlled source ELF injection. Where natural Schumann excitation provides insufficient signal coherence, the DRGN-ELF network deploys controlled ELF sources. Grounded horizontal electric dipole transmitters operating at 10 to 80 Hz with transmitter lengths of 10 to 100 km and power levels of 10 to 100 kilowatts. Such transmitters are operationally mature. The U.S. Navy ELF communication system operated a 76 Hz system with 28 km antenna length. The CSE-LF method for deep mineral exploration has demonstrated coherent ELF signals at 300 km range from 10 kilowatts transmitters. The differential phase measured between two receiving stations for a controlled source ELF signal is where K equals 2 pi f, Vp is the wave number at the transmitted frequency, f is the differential end source to receiver distance, and PSS is the phase anomaly due to lateral crustal conductivity contrasts along the path. By simultaneously measuring PSS during quiet crustal periods, and subtracting it as a baseline, time variations dPSS during active deformation provide the real-time crustal strain proxy needed for the SGE correction term. 5.3 Lithosphere-atmosphere ionosphere coupling. The electrokinetic mechanism for crustal ELF emission is well established. Pore fluid motion driven by seismic stress perturbations generates charge separation at grain boundaries, producing a bulk current density J equals alpha E P pore, where alpha E is the electrokinetic coupling coefficient and P pore is nabla. The pore fluid pressure. This current drives ELF electromagnetic radiation that couples upward through the atmosphere into the Earth ionosphere waveguide. Numerical studies of this laic mechanism have demonstrated that ELF emissions associated with crustal stress changes propagate globally at propagation rates of approximately 0.1 decibels per megameter and are detectable at distances exceeding 5,000 kilometers from the source. The DRGN-ELF network exploits this coupling in reverse. By measuring the ELF signature of crustal deformation at geophysically known locations, it constructs a real-time map of the electrokinetic current density field, which is then used to correct the geopotential measurement in the SGE. 6. Geophysical applications. 6.1 Slow slip event detection. Slow slip events are quasi-aseismic episodes of fault creep lasting from hours to years, occurring primarily at the down-dip extension of seismogenic megathrust zones. They release accumulated interplate strain without generating damaging seismic radiation but are epidemiologically correlated with the nucleation of large earthquakes. Current detection relies on GNSS geodetic networks that resolve daily displacements of approximately 1 mm, blinding the scientific community to SSEs shorter than several days or smaller than MW approximately 6.0. DRGN-ELF addresses this detection gap through two complementary channels. First, the optical clock comparison resolves geopotential changes equivalent to 0.7 mm height change at 1 hour cadence, allowing SSEs to be detected when they begin, not after several days of GNSS accumulation. Second, the ELF phase perturbation from the electrokinetic response to SSE fluid pressure changes provides an independent, higher cadence alert channel. Together, these channels enable the first continuous, sub-hour detection of SSE initiation. 6.2 Hydrological mass loading. Continental water storage changes impose geopotential perturbations up to tens of centimeters in height equivalent, varying at weekly to annual timescales. GRACE-FO resolves these changes globally at approximately 300 km spatial resolution and 30-day temporal resolution, insufficient to resolve sub-regional groundwater depletion or abrupt permafrost drainage events. The DRGN-ELF network provides complementary local to regional geopotential monitoring at less than 10 km spatial resolution and sub-daily temporal resolution, precisely filling this spatio-temporal gap. 6.3 International Height Reference Frame Densification. The International Association of Geodesy established the International Height Reference Frame as the global standard for vertical coordinates, requiring geopotential numbers at reference stations with 10 squared square meter per square second accuracy globally. At present, non-fiber sites cannot be tied to the IHRF at this accuracy level. DRGN-ELF, by using ELF waveguide propagation as the transfer channel rather than optical fiber, extends chronometric leveling to any location on Earth reachable by seismic-grade borehole drilling, including mid-ocean islands, subpolar regions, and active volcanic environments. 7. Novelty, claims, and distinction from prior art. 7.1 Claims of independent inventorship. IP Claim 1, the Seeley geodetic equation. The measurement equation delta U, C squared equals minus integral VL dt minus delta ELF IJ. Combining chronometric leveling with cryogenic rotation subtraction and an ELF-derived crustal strain correction, is an original intellectual contribution of Chris D. Seeley, first disclosed herein. IP Claim 2, ELF-mediated geopotential coupling modality. The use of differential ELF waveguide phase measurements as a real-time crustal strain correction term in a chronometric geodesy network. Enabling geopotential recovery independent of fiber links or satellite uplink is an original intellectual contribution of Chris D. Seeley, first disclosed herein. IP Claim 3, DRGN-ELF network topology. The three-tier network architecture combining borehole optical clock nodes, surface ELF receiver stations, and optional space-borne phase reference in a single-phase coherent loop with the Seeley geodetic equation as the fusion algorithm is an original intellectual contribution of Chris D. Seeley, first disclosed herein. IP Claim 4, electrokinetic calibration protocol. The methodology for empirical determination of the site-specific electrokinetic coupling coefficient eta via concurrent ELF, seismic, and clock comparison measurement during calibration campaigns, and its subsequent use as a real-time correction coefficient in the SGE, is an original intellectual contribution of Chris D. Seeley, first disclosed herein. 7.2 Distinction from joint prior art. The foundational hardware used in DRGN-ELF, the QLAG maser, BBG-SVG gyroscope, and MANSA thermal skin, was disclosed jointly by Chris D. Seeley and Brad Yocum in the QLAG, BBG-SVG, MANSA provisional filings. Those disclosures do not teach, anticipate, or suggest the following elements, all of which are contributed independently by Chris D. Seeley. Application of the BBG-SVG rotation sensor to differential geopotential recovery via the SGE rotation correction integral. Use of ELF waveguide phase as a geodetic correction channel. The borehole deployment geometry for optical clock nodes, including the MANSA thermal adaptation to 40 to 80 degrees Celsius borehole environments for geodetic purposes. The three-tier DRGN-ELF network topology and associated data fusion algorithm. The concept of electrokinetic ELF calibration for geopotential recovery. 7.3 Distinction from prior chronometric geodesy literature. Existing chronometric geodesy literature demonstrates geopotential recovery via optical clock comparison, but uniformly assumes fiber optic or free space laser time transfer, and none incorporates ELF waveguide coupling or cryogenic superfluid rotation subtraction. The existing CSELF electromagnetic exploration literature demonstrates ELF crustal conductivity mapping, but does not combine this with clock-based geopotential measurement. No prior work discloses the combination claimed here. 8. Discussion, rigor, limitations, and future work. 8.1 Outstanding calibration requirements. The electrokinetic coupling coefficient eta is the largest source of model-dependent uncertainty in the SGE. Laboratory measurements on representative rock samples yield alpha-E values spanning 3 to 4 orders of magnitude depending on porosity, fluid saturation, and temperature. Translating laboratory scale alpha-E to the kilometer scale network path integral alpha-E dl requires tomographic inversion of the crustal conductivity structure using independent datasets. This calibration effort is the primary experimental program required before DRGN-ELF delivers operationally certified geopotential data. A staged deployment is therefore recommended. Phase 1 establishes the clock-to-clock comparison over a well-characterized fiber link at a site with concurrent ELF monitoring, validating the SGE rotation correction and measuring eta against ground truth leveling data. Phase 2 extends to non-fiber sites using only ELF as the time transfer adjunct channel, with the fiber site serving as the validation anchor. 8.2 Ionospheric perturbation management. The principal interference channel for ELF geodesy is ionospheric variability. Geomagnetic storms, solar flares, and anthropogenic HF heating events can alter the D-layer height by tens of kilometers on timescales of minutes, shifting the ELF phase velocity by up to 5% and introducing apparent differential geopotential signals of several centimeters. The DRGN-ELF system manages this through 3-node over determination of the local waveguide height, integration of real-time ionospheric tech maps from GNSS networks, and a data quality flag system that suspends ELF correction during geomagnetically disturbed intervals, falling back to uncorrected chronometric leveling. 8.3 Path toward operational deployment. A minimum viable DRGN-ELF demonstration network would consist of 3 borehole nodes at approximately 100 km spacing in a geologically well-characterized region with existing GNSS and seismic instrumentation, the Cascadia subduction zone. The Iberian Peninsula or the Aegean volcanic arc are natural candidates. Each borehole node requires a capital investment comparable to a modern deep drilling project. But the geodetic return, continuous, sub-millimeter height monitoring with SSE sensitivity, significantly exceeds the capabilities of existing GNSS, INSAR networks for tectonic applications. 9. Conclusions. This paper has presented the DRGN-ELF system concept in sufficient theoretical and engineering detail to establish scientific priority and enable independent evaluation. The central contributions are: 1. The Seeley geodetic equation, which rigorously combines chronometric leveling, cryogenic Sagnac correction, and ELF crustal strain compensation into a single measurement model capable of sub-millimeter geopotential resolution at 1-hour integration. 2. The identification of the Earth ionosphere ELF waveguide as a globally coherent geodetic phase reference, enabling chronometric leveling at sites unreachable by optical fiber or with restricted satellite access. 3. The application of Professor Kivelson's framework for topologically protected macroscopic quantum order to justify the qualitative superiority of the BBG-SVG superfluid vortex gyroscope as a rotation reference in precision chronometric geodesy. 4. A 3-tier network architecture and calibration protocol that provides a clear path from proof of concept demonstration to operational geodetic deployment. Taken together, these contributions define a new modality in geodesy, ELF-coupled chronometric geopotential monitoring, whose full scientific exploitation will require the multi-year calibration and deployment program outlined in Section 8. The intellectual framework and IP priority are hereby established under the primary inventorship of Chris D. Seeley. References: Achterberg, D.F., Davis, J., Edkins, S.D., Fradkin, E., Van Harlingen, D.J., Kivelson, S.A., Lee, P.A., Radzahovsky, L., Tranquita, J.M., and Wang, Y. The Physics of Pair Density Waves, Cuprate Superconductors and Beyond. Annual Review of Condensed Matter Physics, 11, 231-270. Birhamar, A. On a Relativistic Geodesy. Bulletin Geodesy, 59, 207-220. D. H. Fu, C. Zhang, J. and Huang, Q. Numerical Study of Global ELF Electromagnetic Wave Propagation with Respect to Lithosphere-Atmosphere-Ionosphere Coupling. Remote Sensing, 13, 4107. Fradkin, E., and Kivelson, S.A. Pneumatic Fermi Fluids in Condensed Matter Physics. Annual Review of Condensed Matter Physics, 1, 153-178. Grati, J., Collar, S., Vogt, S., et al. Geodesy and Metrology with a Transportable Optical Clock. Nature Physics, 14, 437-441. Kivelson, S.A. Award citation available at Kivelson, S.A., Prabhu Goel Family Professor, Department of Physics, Stanford University. Research Program: Emergent Properties of Strongly Correlated Quantum Mechanical Many-Body Systems. Costantino, G., Gifford Rowason, S., Radige, M., et al. Slow slip detection with deep learning in multi-station raw geodetic time series validated against tremors in Cascadia. Archive, 2305.19720. Liu, D.X., et al. Measuring intercontinental scale geopotential difference using atomic clock frequency comparison with PPP technique. Science Direct. Melchtabler, T., Grosch, G., Lisdat, C., Schmidt, P.O., and Denker, H. Atomic Clocks for Geodesy. Reports on Progress in Physics, 81-064401. Packard, R.E., and Vitali, S. Principles of Superfluid Helium Gyroscopes. Physical Review B, 46, 3540. Seeley, C.D., and Yocum, B. QLAG Lagrange Point Maser Network, BBG-SVG Superfluid Vortex Gyroscope, and MANSA Adaptive Nanocarbon Thermal, RF Skin. Provisional Patent Filings, May 2026. Seeley, C.D. Differential Relativistic Geodesy Network with Cryogenic Inertial Reference. Provisional Disclosure, May 2026. Shen, Z, et al. Measuring intercontinental geopotential differences by synchronizing optical clocks. Physical Review Letters. Takano, T, Takamota, M, Ushijima, I, et al. Geopotential measurements with synchronously linked optical lattice clocks. Nature Photonics, 10, 662-666. Velikov, E.P., et al. Underwater Electromagnetic Sounding System. Controlled Source ELF Method. Geoelectromagnetics Research Institute. Inventorship Affirmation and IP Notice. Inventorship Statement. The Foundational QLAG Lagrange Point Maser, BBG-SVG Superfluid Vortex Gyroscope, and MANSA Adaptive Nanocarbon Thermal, RF Skin technologies are acknowledged as jointly invented by Chris D. Seeley and Brad Yocum. The inventorship of those works is not altered or claimed herein. The following are claimed as the sole and independent intellectual contribution of Chris D. Seeley. The Seeley geodetic equation and its derivation. The DRGN-ELF network topology and three-tier architecture. ELF-mediated differential geopotential coupling as a geodetic measurement modality. The electrokinetic ELF calibration protocol for the SGE correction term. Application of the Kivelson topological order framework to justify cryogenic vortex gyroscope superiority in geodetic contexts. Borehole optical clock deployment for geodetic differential relativistic leveling. This document constitutes a public prior art disclosure establishing the priority date of June 2026 for a patent application on the DRGN-ELF system and method to be filed in the name of Chris D. Seeley. All rights reserved. No license, express or implied, is granted to any party by reason of this publication.